Tech Talk series by engineers for engineers. And I'm Kannan Muthukkaruppan, one of the co-founders at Yugabyte. And it's my pleasure to welcome again Srini, who's done, I think, at least one, maybe more of these Friday Tech Talks. But Srini, welcome and thanks for joining today. Why don't you introduce yourself and then the topic for the day as well?
Yeah. Hi, Kannan. Hello, everyone. I'm Srini. I'm part of the field engineering team based off Chennai, India. I'm been with Yugabyte for more than 2 years now. As part of the field engineering team, our job is to work closely with customers and partners, understand the challenges, their OKRs, making sure that they are successful in their journey. I'm glad to be here to share my humble thoughts on enhancing application resilience using adaptive retry policies. All right, let's get started. This is just to give you a perspective of how an application integration architecture with YugabyteDB may look like, right? So this is one of the integration patterns. So in this case, multiple application services are connected to the YugabyteDB cluster. Again, depending on the requirement, sometimes you may go with 1:1 mapping between application and the database. So in this case, I mean, more from an understanding standpoint, as well as the complexity of the distributed systems in general. So I've depicted multiple application services connected to the database itself. Again, if you look at each of these applications, again, each of these applications have multiple replicas of it talking to the same database itself. And more from a database cluster standpoint, it's a cluster of 4 nodes, just more from a representation standpoint, depicted 4 nodes here. And then some of the critical database processes are also listed here, right? And we run this cluster on commodity machines, and the processes in all these nodes interact with each other over the network, right? Sometimes, I mean, sometimes we take it for granted, some of the fallacies of distributed systems per se, right? So always, it's a misbelief that the network is always reliable, the latency is always fixed, the bandwidth is unlimited, the systems are always stable. That's not the case, right? So the network is not at all reliable, right? So, and the missions could fail. So if you really want to build a robust, resilient application, so that means that we need to factor in all these different exceptions that may potentially stem out of any of the moving layers in this application architecture, right? So, I mean, just to give you more perspective, I've listed some of the common exception parts here. The failures could be transient. It could be because of network glitches. You might see RPC timeouts. System may be overloaded, so it may not be accepting any incoming requests. Because of that, the request could fail on the in the application layer, or it could be related to infrastructure failures as well, commodity machine failures and whatnot, right? Or sometimes connection related issues, connection timeouts, or connection pool exhaustion. All this could happen in a real-time application, right? Sometimes it could be a valid application-related transaction issues as well. So that may happen because of transaction conflicts or schema mismatches and whatnot, right? And some of the failures could be because of planned system events like scale out or upgrades or rollout that might interrupt some of the incoming requests. Like maybe the ratio may be very minimalistic, but still you might see some disruptions, right? The idea of this slide is to essentially sort of justifies the need to have application retry so that we would be able to mitigate all these exceptions that could potentially coming out of these different transient failures, right? So in this, I've listed some of the most common SQL states and exceptions. We'll try to go over all these different exceptions. So I'll try to cover as much as I could. We sort of simulate all this different exception path. We'll try to understand when exactly these exceptions could arise and what could be the state of the application when these exceptions happen, and how we go about addressing those exceptions as well.
And maybe I would just make one point that even with traditional, like say single node relational databases, building a resilient, highly available application necessitates some of these best practices. but it in a distributed setup, especially one built for on commodity architecture, shared nothing architecture, there are more moving parts, and the expectation that when you do say a software upgrade and things like that, when there's a lot more mobility in the system, this becomes even more important than in traditional databases. But these are just good best practices in even traditional single node databases. Would you agree, Srini?
Yeah, yes, Kannan, absolutely. Yeah. So what we are going to, what I intend to do is, because in order to simulate these exceptions, of course, we could take a real cluster distributed across multiple nodes and physical machines, but simulating these scenarios would generally be time consuming. We may not be able to finish it within the given time period, right? So that's a reason I am bringing up a cluster in my local machine. So it's a RF3 cluster. I have brought it up using Yugabyte. That's one of the ways how we can quickly get a Yugabyte DB cluster up and running, right? And also I've written a simple web application, essentially a CRUD application that exposes a bunch of REST endpoints. So we would be invoking those endpoints, and then we'll try to simulate all these different exception paths, right? And the application is written in Java using Spring Boot framework. It's pretty straightforward. More from a connection standpoint, purposefully I've kept so I'm using Hikari as the connection pool here. Purposefully I kept the pool limit, min and max limit as 2, so that that gives us the flexibility to simulate all these different exception paths, right? And then I'm using YugabyteDB smart driver. So, and then I've given 2 endpoints here. So like I mentioned, it's an RF3 cluster with listening at .2, .3, and .4. So these are the 3 instances. So I've specified it in the connection string person. So let me start the application. All right. So the DB cluster is already up and running. I've just started it, and it's all 3 instances are healthy, and the application is also up and running. All right. So I'm going to send send a GET request to one of the HTTP endpoints. And this is going to get a list of to-do items, right? And I've kept a breakpoint in the application code. So what has happened so far is like we have already established the connection successfully, and it has set the DB cluster to fetch the result, which needs to be iterated and then populated in the domain object, and then we'll send the response back, right? So let's look at the established connections to the database per se, right? So if we look at the bottom window, so like I said, the connection pool has 2 connections. These 2 connections are established against .3 and .2. Right now, .2 is idle, not being used. .3 is the active one, was the active one, in fact, since we have kept a breakpoint there. So now it's idle in the middle of a transaction, right? So think of like a planned system event, right? So while you were using the cluster in the middle of the business, you might roll out a version upgrade, or you might do a rolling restart of your service, and so on and so forth. Though the database, the service side does its best to handle these things gracefully. So most of the time, the active connections would be handled gracefully, but you might have certain connections. So idle connections, we don't need to worry about it. In case idle connections get disrupted, the pool would pool would fix it. But those connections that are idle in transaction, in case these connections get disrupted, then you're going to see exceptions in your application layer, right? So I'm going to simulate the same thing here, right? So because the connection, the request is right now being serviced by .3. What I'm going to do now is I'm just going to stop 127.0.03 instance, right? So the instance is stopped right now. So if I check the connections again, the connection is gone, right? Because the instance is stopped and the physical socket connection will lose the physical socket connection, right? So if I resume the execution flow now, so we hit the exception block, right? So in this case, the retry logic is already written. It's a very simple, I'll go through the policies as well. So the exception, the flow is, so when there is an exception, it will be matched based on this SQL states. So these are the SQL states I've listed, I've shown in the deck itself, right? So I'll go through all these SQL states. The purpose of these different simulating these exception paths is to understand various scenarios and then when exactly these scenarios happen and how we go about addressing them, right? So in this case, since we have stopped the node and there was a connection which was, it was a in-flight request in the middle of being serviced, and sort of it gets disrupted, right? And if I look at the SQL state itself, so in this case, the SQL state is 57P01, and which is matching our condition as well. 57P01 is part of our list. And the error message is saying that terminating connection due to unexpected postmaster exit, right? So obviously that's the query layer process, which is interrupted because of the node restart, right? So this exception can be safely retried. Of course, this is a GET request.
One question coming, like they're not able, they're able to see the presentation, but not your terminal window.
I see. About now?
Yes, now we can see the terminal window.
All right. Are you able to see the ID as well?
Right now, sorry, yeah, right now I'm able to see the IDE, but not the presentation. So yeah.
Yeah, so I'm moving between IDE as well as the terminal window. So earlier I was showing the terminal window.
Yeah. When you switch, we are able to see it. Yeah.
Right. All right. So right now, yeah. So I was telling, I mean, I put a breakpoint to see this execution flow, right? So when we hit the exception is caught in our try-catch block, and the SQL state is 570.
One more input, like if you're able, are you able to increase the font size?
Yeah.
Thank you.
All right. Yeah. Yeah, sorry for that, because I've opened multiple windows because we need to see all those things in the window itself. So apologies for that. So the SQL state is 57P01 and saying that it's terminated because of postmaster exit, right? So that means that this exception can be safely retried. Of course, this is a GET request sort of idempotent. We can retry this exception, but if it's a write request, we need to ensure that I mean, in the sense, we have to have the right logic in the application layer to be built in so that you can retry those requests again, right? So let's continue the execution here, right? So if I resume the execution again, because the retry logic is built in, so it is going to retry the same endpoint transparently. And then if we go back to the terminal window, and then if I check the established connection, so this time the request is serviced by .2, right? So when we tried the application for the very first time, it was serviced by .3, and this time it's going to .2. So this is being taken care of by the smart driver itself, right? So smart driver essentially maintains a pool of healthy as well as unhealthy nodes, and if you encounter a node failure, it gets blacklisted, and then it ensures that the subsequent connections will be established against the healthy nodes, right? So this time it has been serviced by 0.2, right? As an extension to the previous exception path, what I'm going to do now is, this time I'm going to gracefully terminate the connection. Again, the state is idle in transaction because of the breakpoint, it's in the middle of getting service. So I'm going to send a kill terminate signal, which is -15, to kill this process, right? So to terminate the process, to terminate this process. So the process is terminated now. So if I go back to my IDE and then resume the execution flow, again with the exception block, right? So this time also the SQL state remains the same, but the error message is slightly different because these are all two different scenarios, right? So in the earlier case, the node was stopped. So in this case, the connection has been terminated, right? So it's saying that connection has been terminated due to an administrator command, right? And then since we have retry policy built in, which is a simple retry policy where we try to retry the same transaction for 5 times, and then we'll have some backoff limit as well. I'll cover the backoff limit in a while. So let's continue the execution flow, right? So, and again, we have hit the same block, same GET request block. And then if I go and check the established connections this time it goes to 0.2 again, because 0.2 as a node is still healthy. And instead of gracefully terminating the connection, this time I'm going to kill the connection. So that may happen, right? So imagine your system is sort of momentarily overloaded for some reason, and the operating system OM killer kicks in, and then it cleans up some of the process. As part of that, could potentially kill your connection as well, right? So in the middle of servicing the request, if that happens, so I've forcefully killed the process here, and then if I go and continue my execution flow, so I'm going to hit the same exception block this time, right? So this time the error message is different. And again, because it stopped at this block, because it's matching our error condition as well. So 08006. And it's saying that an input output error occurred while sending it to the backend, right? So that means that it's killed in the middle of serving the request. And then that's the reason we have hit this problem. Because we have the retry logic still in place, we could continue the execution flow. So when you continue the execution flow this time, we hit the same block again. And if I resume it, so this time it should get through without any exceptions, right? So, so we have received the list of to-do blocks, right? And these are the different exception paths related to connections and whatnot, right? So the next one is, what I'm going to do now is it's more about simulating simulating a network timeout, right? So I'm going to set some parameter. I mean, this is like, because everything is running in my local machine, so I'm not going to use any external tool to simulate network delay between the nodes, but that is a test flag, G flag, through which we can simulate the network timeout flow, right? So I'm going to sorry. Yeah, it's taking some time. Yeah, ideally I should have given true. Apologies for that. So what I'm doing now is I'm just setting this G flag in all three DB instances, so that when I go and try the same workflow again, right? If I try the same workflow again, we hit the same get block. Sorry, instead of getting into that get block, so we have hit the exception class straight away. It's because this time the error message, the SQL state is XS000, and says that deadline for query passed, right? So that means that it has timed out. Again, this could be intermittent. And if you, I mean, the way to have the retry logic is, so in this case, I've kept the same retry policies for all these different SQL states and exceptions. Based on your requirement, sometimes you might have different retry policies. So, I mean, certain exceptions, you don't need to retry for multiple times. Rather, you can retry it for 1 or 2 times, and then you have different backoff limits for those exceptions as well, right? So, and what I'm going to do now is I'm going to reset the flag again. So I'm going to change it from true to false. Yeah.
And one example where you may want a different retry policy, just thinking aloud, right? Like suppose you have a multi-step transaction where you said begin transaction, did some insert, did some select, update, whatever. Then if one of those intermediate statements timed out or had one of these errors, then you know that none of the transaction actually committed, right? And in which case, maybe you want to just retry that business transaction. But if the step that hit this issue is the commit step, and right when you were doing the commit statement, you got a network timeout, then you can't be sure in any database, not just Yugabyte, whether that transaction actually committed or not. And in that case, your retry logic may have to have some idempotency check to say, did that, when you restart, whether the new order was already created or things like that. Yeah.
That's correct. Yeah. Yeah. Those are the edge cases where the status may be non-deterministic. So that means that you have to have the logic built in your application to handle those edge cases. So I've reset the flag. So this time it has gone through without any issues, right? And the next use case is more about, so, I mean, let's check the connections here. So we have connections established to 0.4. And RF3 cluster, earlier when we started the testing, we had all three instances up and running. And then we stopped one of the instances, which is instance 2. What I'm going to do now is, there's more of, think of this scenario like, sometimes because of network partition, so you might end up, so see, it's a 3-node cluster, right? So the clients would be connected to all 3 nodes, right? So imagine there is a network partition where you have 2 nodes on one side and 1 node on the other side, right? So more from a client standpoint, you have clients connected to all 3 instances as well. So now the potential scenario is, clients that are connected to the majority side, that would continue to function because the quorum is maintained there. But the clients that are connected to the minority side, right? So now it can't serve the request because it will back off because the quorum is lost. So that means that, yeah, so this is a real potential issue. So one way to handle this is, yeah, so handle this in the application itself and then gracefully show some error message to your end user. If not, you can have some sort of a special retry policy built in the application, which would give a chance to your application to see whether if it's an intermittent network issue, so it could last for only for a few milliseconds or whatnot, right? So if the network comes back again, then your cluster would join the quorum again, right? So then everything would be smooth, right? So those are some of the decisions that you have to take. So it's more about having those retry policies and give your system a chance to recover when these kinds of exceptional cases happen in production, right? So that's what I'm going to do. What I'm going to do now is I'm going to stop the other node as well, right? So we have already stopped instance 2. I'm stopping the instance 3 now, right? So that means that if I try the same endpoint again, essentially, so this is just to simulate the partition, right? So since I brought down 2 nodes, assume that those 2 nodes are in a different partition, right? So in this case, we have clients connected to nodes which are on the minority side, right? So that means that in this case also, we have hit the exception. The SQL state is 08003, saying that Hikari pool connection is not available, right? So the request timed out after five seconds, right? So that's the connection timeout. So Hikari is not able to give you a healthy connection within 5 seconds. So that's an indication that obviously the pool is not able to establish healthy connection to the nodes on the minority side, right? So let's say your network recovers. So that means that I'm going to bring back one of the nodes, right? So if I start the node again, okay, so the node has come back online. So if I go and resume this exception path, this time it gets through without any exception, right? Because the node is back, so the quorum is retained. So that means that if I go and check my connections again, it's been serviced by 02 now, right? And then this path would get through without any issues, right? So it's good to have these edge cases handle in your application as well. So as much as possible, you give a chance in the application layer to see if can be recovered if it's a momentary network glitches or whatnot, right? And the other one is, so far we have seen the transient errors that could happen because of network timeout or connection related issues or whatnot, right? And that could be valid transaction related issues as well. For example, let me bring up the other node as well. When this comes up, I'll connect via YSQL SH terminal. So this time we'll look at all right. Okay, let's list the to-do from to-do table. What I'm going to do now is via this YSQL SH terminal, I'm going to select this row. I'm going to log this row, right? So let's begin the transaction and then start from to-do where ID equal to this for update, right? And if I try to update this row, whatever the row that I picked, right? So if I try to update this row from the application, so by default, in this case, I'm using snapshot isolation. So snapshot isolation favors optimistic concurrency, right? So it's more about fail fast, right? Since the row is already locked, so if I try to update the same thing from the application, let me get that. If I update the same thing from the application, let me replace the UI. So if I send the put request again, yeah. So this is going to hit the save block here, right? So this is the update path, right? So earlier we were looking the get request. So this time it's hitting the update path. And if I resume the execution flow here, this is going to fail again, right? So this time it's a valid application transaction exception. So it's a serialization exception, right? It's 40,001 and says that it has failed because it could not serialize access due to concurrent update, because we have the same row being locked in a different session. So that's the reason this is failing, because of concurrent update, right? So if I roll back or commit from the other session and then retry the same transaction, it should get through without any issues, right? So the subsequent retry, we hit the same update block, and then if I continue the execution flow, it'll go through without any exceptions, right? So these are all some of the application related exceptions. So 40,001 could happen because of conflicts, or sometimes could happen because of schema changes. For example, if you have opened a transaction, which is a multi-step process, and the middle of the execution of the schema gets changed, then sometimes you might face this 40,001 serialization exception as well. So if you retry the same transaction again, that should go through without any issues, right? So so let's spend a couple of minutes to understand the retry policy itself. So this is, I mean, essentially it has, like I said, you can have multiple retry policies depending on the execution flow or the exception path. And in this case, I've kept two different retry policies. One is never retry. So for some of the persistent errors, you don't want to retry, because even if you retry, nothing is going to change. And for other transient errors, it makes sense to retry those execution flow, right? And it has been augmented with back off limit as well. So in this case, it will retry for 5 attempts, and then with a back off limit of 5 seconds, right? So that means that even when you retry it, you do not want to retry it forever, right? So there has to be some limit as well. And at the same time, you should not retry continuously as well, right? So because if you have multiple connections, if those connections hit the same error, and if you retry it, then you end up bombarding the system, right? So that's the reason it's always good to have some back-off limit, so that it is stretched over a period, so that you give some you give some cool off time for the server to recover from these failure cases as well, right? And the last one is, I just wanted to show you the deadlock related exception as well. So
one question,
yeah.
Srini, coming is, does
Yeah.
the retry policy depend on which driver you're using? And I'm guessing.
No.
Okay.
Right. I mean, in this case, this happens to be written in Java. So in a similar way, we have to have the logic to be written for other language runtimes as well. But it is not dependent on the driver per se. I mean, in the sense, we could have the same thing with Postgres driver as well. I mean, I happen to use the YugabyteDB driver so that I could show some of the failure scenarios. in terms of what YugabyteDB smart driver does in those failure scenarios. But with Postgres driver, you can specify all those different endpoints so that it should be able to load balance across those endpoints.
And similarly, the other language drivers also would have similar mechanisms.
That's good. Yeah. All right. So this time I'm going to bring up the cluster in read committed mode so that we can look at the deadlock exception. So destroy the cluster. So I'm recreating the cluster in read committed mode. Let me stop this process so that I'll give some resources back. All right. Yeah. So while this comes, let me finish the rest of the slides as well, and then we can come back to the deadlock exception. So like I mentioned, it's always good to watch out for these SQL states and some of the transient as well as recoverable exceptions in your application code. So what you gain is, the retry policy should be properly defined, and you have to define it with appropriate limits and backups. And then make sure that you distinguish between transient versus persistent versus business errors, right? So valid business errors need to be propagated to the upstream systems per se. Persistent errors, there is no need to have the retry logic to be built in because those are permanent errors, so need to be handled in a different way. And transient errors can be retried with those retry policies. And then observe and adjust is important because you have to track the effectiveness of the retry policies. Time and again, make sure that whether you have put the right limits in place or not, whether you have put the backup limit, sometimes it may be on the higher side or sometimes maybe on the lower side, depending on few exceptions, you might have to adjust it again and again. Make sure that you track the effectiveness of it, right? So by doing so, what essentially we do is we improve the overall resiliency of the system, which leads to an enhanced user experience, and then reduce error rates, right? So that's what ultimately we want to do. And this is more important, especially in distributed systems. Like I mentioned, any of the layers could fail at any given point of time. So we really want the application architecture to be resilient. Then it's always good to have this application retries built in such a way that we should be able to mitigate all these different exceptions that could happen in a real production system per se. All right. So the cluster is up and running. So let me connect. Let me open two different terminals. Sorry, two different sessions. And yeah, in the interest of time, so let me copy that. What I'm going to do is I'm going to create two tables, test and test one. And then, so we have two different sessions. So in the first session, I'm going to execute this. So this is more about, I'm selecting from test table for update where key is 1. And then in the other session, I'm going to do the reverse, right? So instead of selecting from test, I'm going to select the row from test 1. And then as part of the same transaction itself, so we have already, this could happen per se. So we have already selected a row from test, and as part of the same transaction, I'm trying to update a row in test 1 for key K1, right? So which has already been locked in a different session, right? So if we do the reverse in this session, so this would fail immediately because this is a deadlock, right? So, and these two sessions have already locked the row, and we are trying to update the rows being locked by the other sessions in two different terminals, right? So when a deadlock happens, it gets detected. So one of the transactions will fail, the other would get to. And then if you commit this transaction, and then if you have retry logic in your application, then you retry it out in the next attempt, most likely it should get through, right? So, and the code for deadlock is that is also listed in the same file itself. So the code is 40P01. So for serialization, it's 40,001, and for deadlock, it's 40P01, right? So, and the descriptions are also given in the repository, and I've given the link for the source code here. So if you want to give it a shot, please feel free to do so, and we'll also make sure that we keep that repo updated as we come across any of the new errors or exceptions that need to be handled in the workflow.
Yeah. Do you have any other slides, Srini?
No, that's the last one, Kannan. Yeah.
No, thank you so much, Srini, for a excellent tour of common errors that can happen in systems, and guided tour on best practices around building highly available and resilient applications and leveraging the max out of your available and resilient database. That was very helpful, I hope, to the audience. And see you all next week on another episode of the YugabyteDB Friday Tech Talk series. Over to you, Srini.
Yeah. Yeah. Like I said, happy to be here to share humble thoughts. Thanks for inviting me. Yeah. Thanks, everyone.
All right. You all have a good rest of the day and weekend.